to organize
Can I ask just a quick question about the homework before we start?
You have a question for the homework?
Yes, just in the form of the answer for the Fourier series coefficients. Do you care if it's in polar or Cartesian?
Okay, AK, right? I think both will work. Yeah,
Okay.
Yeah, for most of time, for some examples, it is actually real value, so there's no that issue. But depending on which gives a simpler expression, you can choose either polar or Cartesian. Yeah.
Okay, sounds good.
Usually we take polar because think about if your signal is given in terms of exponential or some special signals. By taking the integration, because there's a complex exponential in the formula for calculating that AK, so by nature you will end up with something in the polar form. Yeah, so I think in most cases maybe polar form is more natural.
Yeah, I could see that. There were a couple that I saw simplified pretty nicely to Cartesian, but I just put both.
Yeah, it really depends on the case, specific case.
Okay, sounds good. Thank you.
Yeah. Okay, so let's continue talking about Fourier transform. So this is the Fourier. So this is the Fourier transform that we just introduced. The idea is basically, mathematically this evaluates the projection of your signal of interest onto this complex exponential Fourier basis. And then once you have the transform, this transform gives a spectrum representation in the Fourier domain. Now with this representation coefficients, with this spectrum, we can synthesis and recover the signal by synthesizing all the eigen signals. So by linearly combine all these eigen signals with the associated corresponding spectrum coefficients. And then by doing so, we can recover the original signal. So this is defined as the inverse Fourier transform. And in general, for the Fourier transform, for the spectrum, it is a complex valued function of the frequency, of the angular frequency omega. So when we visualize the spectrum in MATLAB, we usually plot the magnitude and phase separately. And then these are the list of pairs of Fourier transforms. And we have proved some of them in the last lecture. So the idea is to follow the definition of Fourier transform and do the calculations. And these are the examples we discussed last time. And then we started to discuss the fundamental properties of Fourier transform. We have this duality theorem says that if we have a pair of Fourier transform, then taking the spectrum as a signal, the corresponding spectrum of this signal is given by the signal function actually. And then we have this linearity. It's very simple because all these integrations are linear. And we, similar to the Fourier series, we have this time shifting property. So a shift in the time domain will lead to a phase change in the frequency domain. And in particular, this phase change depends on the time shift only. Okay, so this is a constant phase change. It's negative omega t naught. Well, t naught is your time shift in the time domain. And so basically, following this from this property, we can see that if you shift a signal in the time domain, either left or to the right, this will only modify the phase of your spectrum, and it will not modify the amplitude of the spectrum. And on the other hand, we have this very important frequency shifting property, which says that if we modulate your time domain signal by a complex exponential signal, and this complex exponential signal, by the Euler's formula, it is basically cosine omega naught t plus j sine omega naught t. So it's basically sinusoidal signals. So we multiply this signal of interest by such a complex exponential signal, and for the resulting signals, the spectrum is given by shifting the original spectrum by omega naught in the frequency domain. So, and this is a very important property, and it tells us that we can shift the spectrum of a signal by modulating the signal in such a way. Okay. Just multiplying the signal by a complex exponential, and then we can shift the spectrum of the signal in the frequency domain. And in the following slides, we will leverage this property to and discuss its applications in the communication systems. We will see that very soon. And these examples are applications of this property. So we know that in that list of table, we know that the constant signal 1 is paired with the spectrum, impulse spectrum. So this is a pair of Fourier transform. And then by leveraging this frequency shifting property, we can conclude that for this complex exponential signal, the corresponding spectrum is taking the original spectrum and shifted by omega naught to the right. Okay, because we can view this one as 1 times e to the power of j omega naught t. So this is regarded as the xt in the frequency shifting property. So now it's a constant signal. So it's this constant signal times this complex exponential. So the corresponding spectrum is taking the spectrum of the original signal, which is given here, is 2 pi impulse at omega, and shift this spectrum to the right by omega naught. So applying a time shifting, we have omega minus omega naught. Okay, so that's the idea. And on the other hand, if we do e to the power of negative j omega naught t, so, and then this will result in a frequency shift to the left because of the negative sign. So you can equivalently say that the frequency shifting property tells us that a phase change in the frequency domain will lead to a phase change in the time domain will lead to a frequency shift in the frequency domain, right? because xt multiplied by e to the power of j omega naught t. It is like modifying the complex signal xt, modifying its phase by omega naught t, right? This complex exponential only modifies the phase part. Therefore, the frequency shift and the time shift is kind of dual to each other. In the time shifting property, we say that a shift in the time will cause a change of the phase in the frequency domain. And in the frequency shifting property, we have that a change of phase in the time domain will lead to a shift in the frequency domain. So it's kind of symmetric to each other. And then by leveraging these two, so in this example, we just derived the Fourier transform for this pair of complex exponential signals. And then by linearly combine them, by leveraging the inverse Fourier transform, we can derive the Fourier transform for sine and cosine signals. So for example, we know that cosine omega naught t is given by the sum of these two complex exponentials divided by 2, right? So this is a linear combination of two signals. So by the linearity of Fourier transform, we conclude that the spectrum of this one is simply the corresponding linear combination of these two spectrums. And this gives the spectrum of the cosine signal. And correspondingly, you can derive the spectrum for the sine signal. So we can see that for the cosine and sine signal, they correspond to a pair of impulses in the frequency domain. Now, to be more specific, so if xt is cosine omega naught t, then the corresponding spectrum is given here, which is a pair of two impulses in the frequency domain. So one is located at omega naught, and it's positive because the coefficient is pi. It's a positive impulse. So it's right here, pi, and this is omega naught. And the other one is located here, negative omega naught. Okay, so this is the spectrum of cosine. And for sine, the spectrum is a little bit different. So we can see that now the spectrum is complex because we have pi over j. We have this complex unit. So let's look at the amplitude of the spectrum only. Yeah, so the amplitude is still we have two impulses. So it's one is located here and the other is located here. Omega naught and left omega naught. Because by taking the amplitude, we are looking at the amplitude of pi over j, which is essentially pi. And for the other one, we are looking at the amplitude of negative pi over j, which is still pi. So the amplitude spectrum, the magnitude spectrum is the same as the spectrum of cosine omega naught t. However, the phase is different. If we also draw the phase. And we can see that at omega naught, the phase part. Okay, so we are looking at the phase of this complex number. Now multiplying, this is basically multiplying by j, this gives negative j pi. So this is a complex number with only the imaginary part. So it's negative, so the imaginary part is negative pi. Therefore, the phase is negative pi. Sorry, okay, let's look at this. We have a complex number with only the imaginary part, real part, imaginary part. So this complex number is negative j pi, so it's negative pi. And here the phase is negative pi over 2, it's negative 90 degrees. So which means at here, the phase is negative. Negative pi over 2. And here at negative omega naught, the corresponding coefficient is negative pi over j. Now you multiply by j, so you can actually cancel this negative sign. You get j times pi. And this is a complex number located on the positive part of the y-axis. So the phase is positive pi over 2. Okay, so you can see the phase for these two impulses are different. But for the cosine signal, for the cosine spectrum, it is real valued. So the phase is always 0. Okay, all the spectrums are real valued. So they are lying on the horizontal line in the complex domain. So that means the phase are all 0. And because the coefficient is positive, so the spectrum is actually equivalent to the magnitude spectrum. Therefore, you can see that sine, cosine, their magnitude spectrum are the same. It corresponds to a pair of impulses symmetrically located at omega naught and negative omega naught. But their phase are completely different. And this is very intuitive because we know that sine and cosine, they are different by pi over 2 in the phase. So basically we have this maybe this one cosine equals to sine omega naught t plus pi over 2. Yeah, so they are different by a phase shift of pi over 2. So that is why their phase spectrum are different by pi over 2. Okay, so this is the frequency shifting property. And here are further examples. This is another very important application of the frequency shifting property. We call this modulation, and we will see this example. So find the Fourier transform of xt times cosine omega naught t. So you have underlying signal of interest xt. For example, this xt could be a voice signal that you recorded, a human voice, for example. Now you are looking at xt multiplied by cosine omega dot t. So we call this operation modulation in signal processing. Usually, as we discussed in the last lecture, the human voice is usually located in a very low frequency region. So to reliably transmit such signal before the transmission, we usually multiply this signal by a high frequency cosine signal, sine or cosine signal. That is to say, here the omega naught is a very, very high frequency, much, much higher than the human voice, than bandwidth of human voice. Why do we want to do that? We can see from the analysis here. So let's look at the spectrum of this modulated signal. Now, first of all, by the Euler's formula, we know that cosine omega t is can be decomposed into a pair of complex exponentials. So this is the Euler's formula. And then if you look at each part, we have a signal xt multiplied by a complex exponential. And this is directly linked to the frequency shifting property, right? A signal multiplied by a complex exponential. So applying the frequency shifting property, we can conclude that for this one, it is modulated by e to the power of j omega naught t. So by the frequency shifting property, the spectrum is given by taking the spectrum of xt shifted to the right by omega naught. So this is the corresponding spectrum. And for the other one, because we have a negative sign in the phase part, so this is to shift the original spectrum to the left by omega naught units. Therefore, you can see that, for example, if my original signal has a spectrum has a certain spectrum in the low frequency region, and then after modulation, the resulting spectrum is given by, we have two parts. Now one part is to copy the original spectrum and shift it to the right by omega naught. So it's right here, and shift it to the right by omega naught. And the other spectrum is located on the other side. Therefore, you can see that after modulation, after multiplying by the cosine omega naught t signal, the resulting spectrum, the spectrum of the resulting signal now stays in a much higher frequency band, right? This is the frequency axis. Now, previously, the spectrum stays in the low frequency part, and transmitting such a low frequency signal over the air is very difficult. We will suffer from a lot of attenuation. And now we are dealing with a much higher frequency signal. So transmitting such a signal is relatively easier.
Where does the 1/2 in that come from?
Sorry, is there a question? I heard something.
Yeah, where does the 1/2 come from when you're transforming it?
Yeah, great question. That comes from the inverse Euler's formula, right? Cosine omega t equals to summation of these two divided by 2. So you have 1/2 in the inverse Euler's formula. So which means the amplitude should be, let's say this is 1, so here should be 1/2. Yeah. So that is induced by inverse Euler's formula.
I have a question too.
Yep.
You're saying it's easier to transmit at higher frequencies?
Yeah,
That's
think
why we-
about the wireless Wi-Fi signal. They are operating at 2.4 gigahertz or no, even higher frequency bands, right?
Yeah, I think that makes sense. Yeah.
Yes, I don't remember, but there is a physics law saying that the attenuation, if you are transmitting a signal, sinusoidal signal with frequency f, the attenuation coefficient is inverse proportionally to the frequency, to the power of 2 or 3. So which means if you are transmitting higher frequency signals, the attenuation is smaller, so you can transmit signal for a longer distance.
What's
Sounds like-
the, what do you mean by attenuation?
Attenuation means that if you transmit, if you transmit sine omega t signal over a distance over 100 meters, so what is the attenuation factor when you receive the signal 100 meters away, for example? So it is like when the signal is transmitted for a certain amount of distance, the signal will get attenuated or in the air.
Oh, okay.
Stops. Yes.
So it's like the degree to which it kind of starts to bounce off different stuff? Or the resistance between one place and another where it gets transmitted? It's like how much it is resisted throughout there?
Yes.
Okay.
Yeah. So that's why we usually, before transmitting any signals, because the signals that we are looking at may be usually in the low frequency, like voice, for example, voice, when you're making a phone call. Before transmitting that, we do such a modulation. And then the wireless signal is actually operating at a very, very high frequency. And the operation that we are doing is simply multiplying the signal by a very high frequency cosine signal. And this Fourier transform property tells us that if you do that, then the spectrum is simply copied and shifted to a higher frequency band. So it's like the signal still remains the same, but we're just moving it to a higher frequency band. And then you can imagine that on the receiver side, once you receive such a high frequency signal, you need to do a demodulation and shift the spectrum back to the low frequency region so that you can recover the voice signal and you can hear that using your ear. Right. So this is a modulation, transmission, and demodulation process, a very standard component in the wireless communication system. We will have one example later talking about this. But you can see that the frequency shifting properties is basically a fundamental technique for the signal modulation in the wireless communication. And then we can further, we can actually apply Fourier transform to a periodic signal. Right? So remember that for periodic signal, we can do Fourier series. And to handle aperiodic signals, we introduce the Fourier transform. But actually, we can still apply Fourier transform to analyze periodic signals. So the idea is that if you have a periodic signal, then we first do a Fourier series decomposition. So this is the lecture 5. And now we apply Fourier transform on such a infinite summation series. And if you look at now by the linearity of Fourier transform, we can just look at the Fourier transform of each of the signal components. If you look at each of them, it is basically a constant. Is a constant AK, the spectrum AK multiplied by a complex exponential signal. So by the frequency shifting property, we have shown that the spectrum for this, the Fourier spectrum for the complex exponential signal is given by such a impulse signal in the frequency domain. Therefore, it's 2 pi times such a shifted impulse. Therefore, the Fourier transform spectrum for periodic signals is given by such a periodic impulse in the frequency domain. Okay, so this is an example that we just discussed called the amplitude modulation. So here's the setup. We are modulating a baseband signal, low pass signal, which simply means the signal stays in the low frequency region. So we are modulating a baseband signal AT to a carrier frequency cosine 2 pi FC T. This carrier frequency is the omega naught that we talk about here. It is the frequency where you want to transmit in the wireless communication channel. For example, if you want to transmit in the 2.4 gigahertz channel, then you should consider FC to be 2.4 gigahertz. Okay, so how do we do that? We simply multiply the baseband signal AT by such a cosine signal with the desired carrier frequency. So you can choose which carrier frequency to use based on your hardware. For example, we want to transmit such a baseband rectangle signal, a very simple rectangle signal. And it is a baseband signal because by Fourier transform, we have shown that the corresponding spectrum is a sinc, looks like a sinc function. And for this sinc function, we can see that the majority part of this signals are concentrated in the low frequency part. So it is indeed a baseband signal. Okay. Now we want to transmit it at the carrier frequency. So we multiply such a rectangle signal by a high frequency cosine signal. And you can see that multiplying a rectangle by a higher frequency sine signal will result in such a signal. So it's like the cosine wave is only occurs within the signal duration. Because everywhere else the signal is 0. So you got such a truncated cosine signal in the time domain. And then by this result, we can conclude that after this modulation, the spectrum of such a truncated cosine signal looks like this. It is basically shifting the original spectrum to the right by the carrier frequency and shifting the spectrum to the left by the carrier frequency. So you get a pair of spectrums. They are located at symmetric locations. And moreover, the amplitude, now originally the peak is 1. So the amplitude is scaled by a factor 1/2 due to the Euler's formula. So now the two spectrums have relatively smaller amplitudes. But in the end, after this modulation, you can see that now this signal is located in the carrier frequency band, and then you can feed it to the wireless communication system, send it over the air.
A quick question.
Yeah, go ahead.
So the sync omega over 2 pi, that's the modulated, or that's the signal being modulated?
Now, this is the corresponding spectrum of this rectangle signal.
Oh, okay.
This is the pair of Fourier transform that we discussed in the last lecture.
Right, okay, I gotcha.
And after modulation, the signal in the time domain, the signal looks like this. And then correspondingly in the frequency domain, the spectrum is given as this one by the frequency shift property.
I gotcha, thank you.
So this is how you modulate a signal to a higher frequency band in the signal processing. Okay, and we have further properties. This is a time scaling property. Well, we're basically saying that if we scale the signal in the time domain by a time scaling factor A, then the corresponding spectrum in the frequency domain is also scaled. There are two effects. First of all, the amplitude of the spectrum will be scaled by 1 over the magnitude of A. And moreover, the entire spectrum will also be scaled by a factor 1 over A. So it's a combination of amplitude scaling and the frequency scaling. And this is very, the following pictures gives a very intuitive illustration. So if we start with such a narrow rectangle signal, you do a Fourier transform, you can figure out that the spectrum looks like this. And you can see that if it is the signal is very narrow in time, but in the frequency domain, it actually, the spectrum spreads over the entire frequency domain. So you have a lot of high frequency components. Now after, and then in the bottom figure, we scale the signal in the time domain. So it's like we are using a time scaling factor A less than 1, so that the time axis expanded. So if we expand the signal in the time domain, then you do the same Fourier analysis. You can see that the corresponding spectrum is still the sinc function, but now in the frequency domain, following this formula, right? Because A is less than 1, so first of all, the amplitude of the spectrum is amplified. So now the spectrum is much higher. And moreover, the scale of the frequency is also squeezed because A is less than 1. So you end up with such a spectrum that is squeezed and amplified. And the intuition is that, imagine that if this signal in the time domain is further squeezed until it becomes an impulse in the time domain. And for impulse signals, we know that the spectrum is given by a constant 1 spreading over the entire frequency domain, right? So if the signal becomes narrower and narrower in the time domain, it implies that the spectrum becomes wider and wider in the frequency domain. So in the end, if this becomes an impulse, then the spectrum becomes a constant value 1. On the other hand, if the signal becomes wider and wider in the time domain, now in the extreme case, this can become a constant signal in the time domain. And for constant signal in the time domain, we know that the spectrum is given by an impulse in the frequency domain. So if the signal becomes wider, it means that the spectrum becomes narrow, more and more narrow in the frequency domain. So this is kind of like a duality in the time domain and the frequency domain. And the intuition is that if your signal becomes wider, meaning that intuitively means that your signal is more likely to be low frequency. So the spectrum will be concentrated in the low frequency domain. Right? If your signal is very narrow, very close to an impulse, that means in order to generate such a signal using Fourier series, we need a lot of high frequency components to approximate this signal. So that's why the spectrum is spreading out over the entire frequency domain. These are very interesting properties of this Fourier transform. Okay, these two, I think they are kind of the same as what we talked about in the Fourier series. Conjugation, this is the same as the Fourier series properties. The conjugate, the Fourier spectrum of the conjugate signal is taking the original spectrum, doing a reversal plus a conjugation. And in particular, if the signal is real valued, then we have this conjugate symmetry property. And also, if we reverse the signal, the corresponding spectrum will be reversed. So these are very standard ones. And this example provides a way to calculate the Fourier spectrum of the two-sided exponential signal by using these properties. So the statement is that given in that list Fourier transform table, we are given that the Fourier transform of this signal is given by this one. This is a one-sided signal. Right? By multiplying by UT, we only preserve the positive side of the signal. So given this Fourier transform, we want to find the Fourier transform of the two-sided version. Now the idea is to observe that such a two-sided signal can be written as a summation of these two one-sided signals. So it's like this is the right-hand side and this is the left-hand side of the signal. And then the Fourier transform of this one is given in the problem statement. So we just need to figure out the Fourier transform of this one. But then this signal is a time reversal of this signal. So you just need to leverage this time reversal property. So by using this property, we conclude that the Fourier spectrum of this signal is simply doing a frequency reversal in the frequency domain. So we just replace omega by negative omega. And then you can derive the result by summing these two. Okay, so in this way, you don't have to go over the definition of Fourier transform. Okay, here's another example which asks for the Fourier transform for this signal. And one way is to, following the Fourier transform definition, do that integration. But it is not easy because integrating this signal and multiplying by that complex exponential is not easy. So the idea is to observe that such a signal, this function looks like the spectrum of this two-sided signal. But from the previous slide, we know that such a two-sided signal has this spectrum. And then this spectrum, the function of this spectrum looks like the signal the signal of interest here. So for example, if you set A equals to 1, then it's 2 over 1 plus omega squared. It is exactly the same as this one, except that we are looking at the frequency domain instead of a time domain. So this motivates us to consider the duality property of the Fourier transform. So basically, from the previous slide, we know that such a two-sided signal has this spectrum. And then by the duality property of Fourier transform, we can directly conclude that if we take this spectrum and make it a signal, so now we are considering this signal, then the corresponding Fourier transform is given by 2 pi times this signal, this function. So it's 2 pi times e to the power of negative omega, the absolute value of omega. So in this way, we can avoid the integral calculations. So it's directly by leveraging the duality property of Fourier transform. Okay, and similar to the Fourier series, we have this differentiation property. Well, looking at the derivative signal, right? The derivative of a signal x, the corresponding Fourier transform is given by a very simple scaling of the original spectrums. Original spectrum multiplied by j times omega. And if you do a higher order derivative, then the corresponding spectrum is given by still the original spectrum multiplied by j omega to the power of n. So you can see that the higher order differentiation in the spectrum domain, they will lead to very simple numerical operations. We know that in general, if your signal is complex, taking higher order derivatives is very complicated in the time domain. But then if we look at this in the frequency domain, then it is very simple. We just take the original spectrum and multiply it by some constant, j omega to the power of n. So this is why later on we will use Fourier transform to analyze differential equations, partial differential equations. Okay. Due to this property, okay, in the frequency domain, differentiation is very, very simple. Simply becomes multiplication. And here's an example, using the differentiation property to find the Fourier transform of xt. Well, the xt is given by such a standard rectangle signal. And of course, you can do it in a standard way by doing the calculation. But here, the observation is that if you take derivative of this rectangle signal, then the derivative signal is very, very simple. From the picture, you can see if we consider the derivative of the signal, you end up with a pair of impulse, because only at this point we have an instant jump. So this will generate an impulse, positive impulse. And then at the location T1, we have instant drop. This will create the corresponding derivatives given by a negative impulse. So essentially, the derivative of xt is given by such a pair of impulse signals. And we know that impulse signals are very simple to deal with in the Fourier transform. Okay, so we have this property. Now, this is an equation. This means left-hand side equals right-hand side. So I can take Fourier transform on both sides. Now, taking the Fourier transform on the left-hand side, we can directly use the differentiation property of Fourier transform. This property. The Fourier transform of this derivative signal is basically the spectrum of xt multiplied by j omega. So it's here, the spectrum of xt multiplied by j omega. And this capital X is what we are looking for. Capital X is the spectrum of xt. So we want to find the Fourier transform of xt. Okay. So this is the left-hand side, and on the right-hand side, we are looking at the Fourier transform of a pair of impulse signals. And for impulse signals, we know they are Fourier transform. So if you look into the table, you will find that their corresponding Fourier transform is given by these two. Okay, so this is an equation on the original spectrum of the signal. So we just solve this equation. Solve this equation, you have this, you end up with this one. And then you can simplify this equation a little bit. So you end up with such a sinc type spectrum. Yes. Therefore, you don't have to go over the definition of Fourier transform. So you can avoid those calculations by leveraging these fundamental properties. And this is another example, which so we are looking at the Fourier transform of such a triangular signal. And this is more complicated if you want to follow the definition, because if you take the integration, then you have to divide this into two pieces. Well, in the first piece, the signal is an increasing line, and the other piece, the signal is decreasing. So you need to evaluate two integrations. And for each of the integrations, it's actually not easy to do numerically. So the idea is to observe that for such a signal, the derivative is very simple. The derivative is given by such two rectangle signals, right? Because in this part of the time domain, the signal is linearly increasing, so the derivative is positive. It's a positive constant with 1/t. And here the derivative is a negative constant, negative 1/T. Therefore, from this signal, we first conclude that the derivative is given by such a pair of rectangle signals. Okay, so first of all, their amplitude are scaled by 1/T, and then in order to generate these two rectangles, we need to move the center of the rectangles to the left and to the right correspondingly. But in the end, this is the mathematical expression. And then we follow the same step. We take Fourier transform on both sides. On the left-hand side, we have j omega times the spectrum of xt. So it's capital X j omega. And on the right-hand side, we need to look at the Fourier transform of these two rectangle functions. And this is not that hard, because from that table, we know that a standard centered rectangle function has this Fourier transform. So we just need to leverage, and then comparing this signal with these two rectangles, you can see that these are just shifted signals. We just have a time shifting factor, T/2 and negative T/2 here. So we just need to leverage the time shifting property of Fourier transform. But specifically, given this one, we know that the time shifted, the Fourier transform of the time shifted signal is given by, is given here. Is this taking this spectrum and modify the phase, multiplying the spectrum by a phase shift component. And for this one, because we are shifting to the right, so the phase shift has a negative sign in it. Okay. So this is the final result. It looks complicated, but if you follow in this logic, you don't have to do any calculations by hand. It's all different combinations of different properties of Fourier transform. And I think in the homework, you will need to leverage some of these properties to avoid intensive calculations. Okay, so are there any questions regarding this example? Okay, so let's move on. Okay, continue. So in the end, you end up with this equation, right? And then you can solve for the spectrum of xt. So you solve for capital X, and then so this is the equation, and then very carefully, so you can take this common factor out. Inside you have a pair of complex exponentials. Okay, this reminds you the inverse Fourier formula, so you can simplify that into a sine. Now, in the end, you got this one, the sine square divided by t omega. And then you divide both sides by j omega. So this is the final result. It's actually a very simple result. Sine square over omega square. But if you want to do this by hand, it's going to be very, very challenging because you have to evaluate very complex integrations. So this is like taking a sinc function and square it. It's sine omega t divided by omega t to the power of 2. Okay, so we have the differentiation property, so we will have this integration property, which says that if we integrate the signal up to time t, then for such a signal, the corresponding Fourier transform is given in this way. It's a little bit complicated, but if you look at each component, it's very simple. Taking the original spectrum divided by j omega. So this one is it's a very simple numerical operation. And then plus such a impulse is pi times capital X0 times impulse. Okay, so for example, if we want to find the Fourier transform of the unit step signal, recall that the unit step signal can be written as the integration of the impulse over t, right? When we introduce the unit step signal, we mentioned this property. So therefore, instead of directly calculating the Fourier transform, we can leverage this property. So ut is the integration of the impulse. Therefore, the x tau here is actually the impulse signal. And for impulse signal, we know that the corresponding spectrum is very simple. It's simply a constant 1 over the entire time domain. Therefore, by this integration property, we just plug in 1 into the spectrum here. So it's 1 over j omega plus pi. Here is still 1 because the entire spectrum of the impulse is a constant 1. So it's plus pi delta omega. Okay, so this delta is caused by the instant jump in that impulse signal. So it looks a little bit weird. And the Parseval theorem, this is the same as what we have in the Fourier series, which says that the form is a little bit different, but underlying idea is the same. So which says that the energy is preserved in both the time domain and frequency domain. So in the time domain, we are looking at the energy of the signal. This is the energy of the signal. In the frequency domain, how do we calculate the energy? We just integrate all the energy densities. So the spectrum, the magnitude of the spectrum to the power of 2 is the energy density. So we are integrating the density over the entire frequency domain. And this is just a normalization factor. But this is different from the Fourier series in the sense that in the Fourier series, we have 1/T for that periodic signal. And here we are taking integration over one period of the signal. Okay. And on the right-hand side, we have summation over the discrete spectrums instead of integration over the continuous spectrum here. So there are some differences between these two, but the underlying idea is the same. And the proof is more or less following the same proof logic. So I will skip it. It's basically, in the first step, you replace this square by xt times xt conjugate. And then both of these two signals can be represented by the inverse Fourier transform. So that's how you introduce the frequency, the spectrum into this integration. And then you can switch the order of these integrations and simplify them. You can get the final result. Okay, so this is the Parseval theorem. And this example is just to confirm such a Parseval theorem. We want to compute the energy of such a simple causal signal. And following the definition of signal energy, we can do it directly. Okay? Just plug it into the signal energy. Calculating this integration, we end up with this result. So this calculation, this approach is the time domain approach, directly integrating the signal energy in the time domain. The other one is, of course, by leveraging the Parseval theorem. So instead of looking at the signal energy in the time domain, we can look at this one in the frequency domain. And to do that, we need to first have the Fourier transform of this signal. So by the Parseval theorem, the signal energy can be also calculated by such an integration in the Fourier domain. But then we need the spectrum of this signal. And this is very easy to calculate. From that list of tables, we know that the spectrum is given by 1/j⍵+a. And then you just evaluate this spectrum. So very carefully, you can see that the magnitude of this complex number to the power of 2 is this one. And then you evaluate this integration, which gives you an inverse tangent function. Okay, and then you keep going, you end up with the same result. But of course, the frequency domain approaches looks more complex for this specific example. This is just to verify the Parseval theory. And in the homework 5, we have one example to show that sometimes it is easier to leverage the frequency part of the Parseval theorem to calculate the infinite series, summation series. Okay, so this is the application of Parseval theorem. Now, the last property is probably the most important property of Fourier transform. So we will use this one to analyze partial differential equations. To analyze LTI systems. Okay, so what is the statement here? Here we are given two signals, xt, ht, and their corresponding spectrum, Fourier transform spectrum. And then let's consider their convolution signal, which is a signal yt defined as the convolution between two. Now the fundamental question is, so the idea here is that, for example, xt is the input signal to the LTS system, right? And h is the impulse response of the LTS system. Then in the lecture 3, or lecture 4, we showed that the output of this system is given by the convolution between these two. And then for such a signal, convolutional signal, we actually have an amazingly simple property. So if we analyze the convolution in the frequency domain, the relation is rather simple. So you take Fourier transform on both sides, you can conclude that, you can prove that the Fourier transform of the output is simply the entry-wise direct multiplication of the corresponding spectrums of x and h. Okay, so in the time domain, these signals are related through the convolution operation. It's very complicated. We have done this in the midterm. In general, it's very complicated to calculate convolution of two signals. But if you transform this into the frequency domain, you don't have to deal with convolution anymore. You just need to look at the spectrum of these two separately and then multiply them together. This resulting spectrum is the spectrum of the output signal. And to get the output, once you have that, you just need to do an inverse Fourier transform to get the output yt. Okay, so in this way, you can completely avoid calculating the convolution. And this is the proof, a very simple proof for this statement. We can go over this, go over the logic. So we start with this convolution. And look at its Fourier transform. Now, by definition of Fourier transform, it is defined in this way. Well, this is basically, this is the definition of convolution between x and h. If you still remember it, right? It's integration x tau ht minus tau d tau. This is exactly the convolution between xt and ht. So therefore, okay, here we are just looking at integration, x convolution ht e negative j omega t dt. Right? If you treat this as one single signal, it is a certain signal defined in terms of convolution. Then this is the Fourier transform of this signal. This is simply the definition of Fourier transform. But then we know that the convolution is mathematically defined in this way. So this big bracket corresponds to the convolution. Okay, now what we do here is that inside we are integrating over tau, outside we are integrating over t. So I can move this x tau to the, sorry, I should, okay, first of all, I switch the order of these two integrations. So now I have dt followed by d tau. So I switch their order. And because I switch their order, so I can leave x tau outside, right? Because inside we are integrating over t, so x tau is a constant. So now we are putting all the other factors that depend on t inside. So we move this one inside, we move this h inside. So this is simply a switch in the order and reorganizing the terms. And then this integration has a very special meaning because let's see what okay, so this is basically the Fourier transform of this signal, right? If you treat this as a signal of t, is this signal integration, this signal multiplied by e negative j omega t dt, a standard definition of Fourier transform. But what is special here is that this signal is a shifted signal. We have time shift tau here. So by the time shifting property of Fourier transform, we know that, okay, the Fourier transform of such a time shifted signal is given by taking the original spectrum of this H and multiply it by this time phase change factor. And so this part is exactly the time shifting property of Fourier transform. All right, and then magically, so first of all, this now becomes a constant for the outer integration, because the outer integration is over tau, so this is a constant. So we pull it outside, we just need to evaluate the rest of the integration. So we put all the rest of the terms together, and magically you can see that this is another standard definition of Fourier transform of X, right? This is a standard definition of Fourier transform. So this is basically capital X, the spectrum of signal X. So you see if you think about this carefully, the reason that convolution now translates into multiplication in the frequency domain is that, now, first of all, we have this time shifting property. We have this time shifting property of the Fourier transform. This time shifting property will give us a phase shift term, and this phase shift term magically contributes to the second Fourier transform. Okay, this one together with the x tau defines the Fourier transform of X. And where does this time shifting come from? This time shifting comes from the convolution, come from the definition of convolution. Okay. Therefore, this is how we transfer the convolution in the time domain somehow into multiplication in the frequency domain. Okay, so this is the proof. It's basically playing with the integrations. Therefore, we can apply this property to analyze LTI systems, because we know for LTI systems, the output is given by the convolution between the input and the impulse response of the system. Now, this is the time domain system equation. So we can take Fourier transform on both sides. Right, we can take Fourier transform on both sides. And this is simply the Fourier transform of Y, your output. And for this one, we just apply the convolution property of Fourier transform. This convolution, Fourier transform of convolution equals to Fourier transform applies to each of them and do multiplication. And this is simply xj omega times hj omega. So in the Fourier domain, the system equation is very simple. We only need to deal with multiplication. Now, once we have the spectrum of the output, in the Fourier domain, you just need to do an inverse Fourier transform to get back to the time domain. If you want a time domain representation. And since in the last step, we need to, in order to get back to the time domain, we need to do an inverse Fourier transform. So we usually you need to check the table for the inverse Fourier transforms. So these two pairs of Fourier transforms are frequently used in the analysis later. So once we have this spectrum, we can, by following this list, we can directly say that the inverse transform corresponds to such a signal. Okay. So in the exams, I will give you the list of tables, so you can check it, and you don't have to compute the inverse transform by hand. So let's look at one example to see how this is applied to analyzing an LTI system. So we are given such a causal input, exponentially decreasing input, and we are given that the system response is this signal. Okay, so and A is not equal to B. These parameters, A and B, they are not equal. So this is a system diagram. LTI system, we have this X, we have the impulse response. We need to find out the YT. Of course, one approach is to convolution, right? In the lecture 3 or 4, standard convolution. But here we are looking at we are going to use the Fourier transform. So first of all, we from this slide, we know that in the frequency domain, the signals, the spectrums are related in this way. So this is the system equation in the frequency domain. Therefore, in order to obtain the spectrum of the YT, we need to calculate the spectrum of input and the impulse response respectively. And this is very simple from the table, because the input and the response, both of them are exponential signals. So from that table, we can directly conclude that the spectrum is given in this way. Okay. So for these standard signals, you can refer to the table. You don't have to calculate the spectrum. Okay, so this is from the table. And now we have these two, the spectrums of the input and the system impulse response. So because this is LTI system, so the spectrum of the output is given by the product of these two spectrums. So you directly multiply them together. Okay, so very simple operation. And then in the last step, you need to do an inverse transform. So now you have obtained the spectrum of Y, the output, right? So the spectrum of Y is given here. This is a specific spectrum. So all you have to do is to do an inverse Fourier transform to get YT. And to do that, we need to actually decompose such a fraction number, big fraction number, into two smaller fraction numbers. And later on, we will introduce a technique to do this. But essentially, you can verify this one, which is in a product form, can be decomposed into the subtraction of these two. So you now have two smaller fraction numbers. And then for each of if you look at each of them, the inverse Fourier transform for each of them is relatively easy, because you can see from this table that this spectrum is paired with such a signal. Okay, so if you do inverse transform, you start with this spectrum, you can directly end up with this signal. So following this table, we can see that this signal, the corresponding inverse transform is given by this exponential signal. And similarly for this one, the inverse transform is given by this signal. Again, because the inverse Fourier transform is linear, so you can do this one by one, term by term. But you need to simplify this spectrum into a form where the inverse transform of each component can be easily identified. Right? If you directly look at this one, it is not clear what is the corresponding inverse transform. So you first decompose it into two smaller fraction numbers. And for each of them, the inverse transform is clear from this table. So this is the idea. So throughout the process, you don't have to do any calculations. Everything you can refer to the existing table of Fourier transform pairs. Was that done by partial fraction decomposition? Yes, exactly. We will, yeah. So some of you may be already familiar with this one. We will discuss this in the following slides. Yes, it is by partial fraction decomposition. Yeah, I think I will stop here. And next we'll talk about the application of Fourier transform to partial differential equations. Okay. So next week is the spring break. So I will see you 2 weeks after that. And if you have any questions regarding the homework, feel free to either come to my office or go to the Zoom. Okay. So enjoying the spring break. Have a nice break.